As promised, this part is going through the handout problems. The first handout problem says that there are two charges. One is plus 8.0 millicuries, or millicoulombs, excuse me. Now you could do this problem thinking that this M represents milli or micro. Normally, a small m is milli, which means times 10 to the minus 3. So this first charge would be 8.0 times 10 to the minus 3 coulombs. And this second charge, and it's plus, and this second charge, or we could use the Q's, Q1 and Q2, is minus 6.0 times 10 to the minus 3. Now, if you translated M as micro, normally I use the symbol mu to designate micro. But if you did that, this number and this number would be 10 to the minus 6 instead of 10 to the minus 3. And on the first one, I'll do both calculations, and then you can fix it. But this says that these attract each other with a force of 3 times 10 to the third newtons. So F is equal to 3.0 times 10 to the third newtons. What is the distance between the charges? Okay, so, and we know that K is equal to 8.99 times 10 to the ninth newtons meter squared per coulomb squared, okay? So K, that's K. So now, we know that the force is equal to K times the first charge times the second charge over the distance between the two squared. So if we solve this, F times K, F times D squared, multiply both sides by D first. So F times D squared is going to equal K Q1 times Q2. Then D squared is going to equal K Q1 times Q2 over F D squared. And then D is going to equal the square root of that, K Q1 Q2 over F. So if we put the numbers in here, D is going to equal K, which is 8.99 times 10 to the ninth, times Q1, which is 8.0 times 10 to the minus 3, and this plus, this is minus 6.0 times 10 to the third, minus third, divided by F, which is 3.0 times 10 to the 3. Doing the math here, you're going to get a negative number, which means they're attracted to each other. Because they're attracted to each other, this is a negative number. I should have put that in here. Because if you put in the original equation here, if you put a negative in here, then you end up with a negative number, and a negative number is consistent with them being attracted. If you get a positive number, then they're by convention. Negative means attraction, and positive means repulsion or repelling. And so if we do the math here, we get 140 to two significant figures, 140 meters. The actual number in the calculator is 143.84, but since all of these are two significant figures, to two significant figures, it's 140 meters apart. Okay, the second problem, and I'll try to do these a little faster now that I went through some of the principles. The second problem, find the electrostatic force between these two separated by a distance of 75 meters in a vacuum. Okay, so all you have to do is plug the numbers into this equation. F is equal to 8.99 times 10 to the 9th times, now this is 2 coulombs, so it's just 2 plus 2, and this is times 5 plus 5, and that's divided by 75 meters squared. To two significant figures, this is going to equal 1.6 times 10 to the 7th newtons. So that's number 2. Number 2 is quite a bit easier than number 1 because you didn't have to do all this here. But once you do this once, you can use it to do the other ones here. Number 3. Two small charged spheres have their centers 0.50 meters apart. So D is equal to 0.05 meters apart and repel each other with a force of the force here, which is repellent, so it's positive, is 5 times 10 to the minus 5 newtons. What would be the force of repulsion if the spheres were 1/10 of a meter apart? So you go to 0.10. Now the best way to do this, in my estimation, is the way we did the other one. Basically what you're doing here is doubling the distance apart. You're going from 0.05 to 0.1. So that's a change of 2 times. And as I told you, the change in force is that number squared. So it's going to be 4 times. Now the question here is it 4 times greater or 4 times less? And if you look, they're getting farther apart, so it's going to be 4 times less. So if you divide this number by 4, you get the answer, which is 4 times less than this. So the force now is 1.25 times 10 to the minus 5. So that's number 3. Number 4. What happens to the force between two charged metal spheres in a vacuum if the charge on each is doubled and the distance between them is multiplied by 3? Okay, so this is just a sort of a thought exercise more than anything else. If you take this equation, and the first thing you're going to do is you're going to double each of these. So this is 2 times greater and this is 2 times greater. So on the top, it's going to be equivalent to the 4 times the original charge on the top. At the same time, you're going to change this by 3 times, which is squared. So it's going to be 9 times the original. 3 squared is 9. And so the change in force is going to be 4 ninths. 4 ninths. The last problem. A sphere, so this one sphere has a mass of 6.0 times 10 to the minus 3 kilograms. And it's floating above a similar sphere, which means it has a similar mass, when both have a charge of 4. So the charges, Q1 is 4 times 10 to the minus 3 coulombs, and the second charge is 4 times 10 to the minus 3 coulombs. Assuming that only the upward force, the electrostatic repulsion, find the distance between the spheres. Now the idea here is it's floating. Okay, so let's draw a picture just so we get a sense of what's going on. And this will, in physics, this is called a force diagram. So you have the downward force of gravity, and at the same time you have the upward force, the upward electrostatic force. And because it's floating, they're not moving, then the downward force of gravity has to equal the upward force of electrostatic force. Now the downward force of gravity is equal to the mass times gravity, the acceleration due to gravity. So that's going to equal 6.0 times 10 to the minus 3 times g, which is 9.8 meters per second squared. This is kilograms. Kilogram meters per second squared is a Newton. Okay, so if you multiply those two numbers together, you get 5.88 times 10 to the minus 2 newtons. And that has to equal this, K Q1 Q2 over d squared. Now, what we need to know here is this distance. And so if we move the distance over, 5.88 times 10 to the minus 2 times d squared is equal to K Q1 Q2, right? That's just multiplying both sides by d squared. And then d is going to equal K, which is 8.99 times 10 to the 9th times Q1 and Q2 are the same, so we'll just write 1.4 times 10 to the minus 3 squared divided by, and this F is going to be, we're going to divide both sides by this, so this F is going to be 5.88 times 10 to the minus 2. And if we do the math here, distance here is going to equal 2.4, two significant figures, times 10 to the 6th meters. 2.4 times 10 to the 6th meters.